Prynhawn da pawb. Good afternoon, everybody. Welcome to session 3 from e-sgol AS Geography. I'm now going to hand you over to Miss Davis, who will take today's lesson. Diolch.
Good afternoon, Prynhawn da, and welcome to the third session for AS Geography. My name is Miss Taylor Davis, and today we will look at Unit 1, Tectonic Hazards. Now, tectonic hazards comes up twice in your 2 years of A-level geography. You will cover this subject for Unit 1, Changing Landscapes, as your Section B. Section A is either coasts or glaciated landscapes, depends which one your school has chosen. But it also pops up in Year 13 in 4.1.1. Now, the content isn't exactly the same. There's some topics added in Year 13, for example, tsunami. But the biggest difference between Year 12 and Year 13 tectonics is the way that you are assessed. In Unit 4 in Year 13, you will answer one 20-mark question out of a possible 2. Whilst in Unit 1 in Year 12, traditionally it's more shorter marked questions, up to 10 marks. I wouldn't be doing it justice if I attempted to cover the entire spec in 40 minutes. So today I will focus on the first section of the tectonic spec 1.3.1, and I will look at the characteristics of the Earth's structure, mechanisms of plate movement, global distribution of plate margins, tectonic processes and hazards, and characteristics of the physical hazard profile that influence its impact, if I have enough time. So this is a simple diagram of the Earth's structure. So formed billions of years ago, the Earth comprises of several layers. Each layer has its own characteristics and purpose. The 4 layers of the Earth include the crust, the mantle, the outer core, and the inner core. Now, this is a slightly more sophisticated diagram with the features A-level geographers need to know. So the surface of the Earth is known as a crust. This is the thinnest layer. I want you to think of an apple and the size of the apple peel in relation to the size of the apple itself. So that's the size of the crust in relation to the Earth. Or if you think of the Earth as a football, the crust would be 0.5 millimeter thick. Oceanic and continental crusts are 2 kinds of crust which are recognized by their thickness, rock composition and placement. The thickness of the crust fluctuates from 3 to 5 kilometers in the ocean basin, while the crust under mainland mountain systems can be 70 kilometers thick. So the average thickness of the mainland continental crust is about 32 to 40 kilometers. When compared to the mantle, the crust layer is comparatively hard, fungible and cold. So oceanic crust is thinner, but it's more dense. That's what I'd like you to take away from this. Here we have an isoline map. Each place along that a line is of equal crust depth. As you can see here, the crust depth is at its highest where there are continents. For example, I can see there that the Himalayas are 70 kilometers thick and Antarctica is between 30 and 40 kilometers thick of a depth. And if you compare that to the ocean, it's averaging around 10 kilometers of depth. An important term in A-level geography is the lithosphere and the asthenosphere. But what is the difference between the two? The lithosphere is composed of both the crust and the portion of the upper mantle that behaves as a brittle, rigid solid. The lithosphere is the outermost mechanical layer, and it's about 100 kilometers or to 200 kilometers thick. The asthenosphere is a solid upper mantle material that is so hot that it behaves plastically and can flow, but it's not a liquid. The lithosphere rides on top of the asthenosphere. So to recap, the lithosphere is the brittle crust on the uppermost mantle. The asthenosphere is a solid, but it can flow a bit like toothpaste or plastically. The boundary between the crust and the mantle is called the MOHOROVICIC discontinuity, or that's this abbreviation. Okay, as you can see there, it's beneath the oceanic and continental crust, but before the upper mantle. The mantle is a dense, hot layer of semi-solid rock, approximately 2,900 kilometers thick, and it contains more iron, magnesium and calcium than the crust. It's hotter and denser because pressure and temperature within the Earth, inside the Earth, increases with depth. The upper mantle consists of two layers. So the layer that's the lower half, between 200 meters down, is the asthenosphere. So this is semi-molten and viscous, and it's capable of flowing slowly. Lying immediately above this is the lithosphere. Okay, so the upper part of the mantle is cooler and more rigid than the deep mantle. Here we have the Gutenberg discontinuity, and this is the boundary between the mantle and the outer core. At the centre of the Earth lies the core, which is nearly twice as dense as the mantle, because its composition is metallic rather than stony. It is comprised of about 80% iron and 20% nickel. The Earth's core is actually made up of two parts. You've got the outer core, which is 2,200 kilometers thick and is liquid, and then the inner core, which is solid and 1,250 kilometers thick. So as the Earth rotates, the liquid in the outer core spins, and this actually creates the Earth's magnetic field. So below the tectonic plates lies the Earth's asthenosphere. Okay, the asthenosphere behaves like a fluid over a very, very long time scale. Okay, there are three main theories on why the mantle moves and why the plates on top of the asthenosphere, which are floating on top of the asthenosphere, is moving. The one on the screen here is convection current. Now, the tectonic plates float on the magma beneath them in the mantle. Convection currents that occur within the molten rock of the mantle act a bit like a conveyor belt for the plates. Tectonic plates move in different directions. The direction of movement and the type of plate margin is determined by which way the convection currents are flowing. So the heat from the core, which is roughly 5,500 degrees Celsius, is transferred to the mantle. Liquid rock close to the core is heated and rises, so the lower part of the mantle, and rises. When it reaches the top, which near the crust, it is forced sideways because it can't pass through the crust. The friction between the convection current and the crust causes the tectonic plate to move. The liquid rock then sinks backwards to the core as it cools, and this process repeats, and that's the convection current. Here we have the ridge pull, and as you can see, we have two plates moving apart here, so that is divergent plate margin. So the ridge push is when the newly formed plates at the oceanic ridges are warm, and so has a higher elevation than the oceanic ridge. The older, more dense, colder oceanic ridge, the either side of the rising new plate. Because the rising magma cools and it's more buoyant and it cools higher than the older, more dense oceanic ridge, gravity causes the highest plate at the ridge to move away from the lithosphere, forcing them apart, and that is ridge push. Here we have slab pull. So cold, dense oceanic plate is subducted beneath the less dense continental plate. The density of the oceanic plate pulls itself into the mantle, and this is called slab pull, which occurs at destructive or convergent plate boundaries. Scientists say that this, out of the three theories, is the one that has most impact on plate tectonic movement. So the lithosphere is split into tectonic plates. The largest plates are the Antarctic, the Eurasian, and the North American plates. Some plates are large enough to consist of both continental and oceanic crusts. For example, the African plate and the South American plate, whilst the Pacific plate is almost entirely oceanic. Plate boundaries are the edges where two plates meet. Most earthquakes and volcanic eruption occur along the plate boundaries. The plates move slowly and inconsistently in relation to each other. Usually, they move around 4 centimeters a year. There are 3 types of movements. The first one is divergent, where the plates are moving apart or away from each other. So these are diverging away from each other, so divergent. The second one here is convergent, where the plates are moving towards each other. And in some areas, we have plates that move past each other, either in different directions or to the same direction but at different speeds, and that's conservative. Okay, first up is divergent plate margin. There are 2 types. The diagram on the screen here is showing 2 oceanic crusts moving apart away from each other. Okay, so this is the oceanic and oceanic version. So diverging plates under oceans, driven by ridge push or slab pull, brings basaltic magma to the surface to form a ridge. Ridge push operates here, where the new magma rising up in the gap is hotter and more buoyant, so rises above the colder, older rock, and then gravity then drives these plates apart. As these plates move apart, this leaves cracks and fissures, lines of weaknesses that allows magma from the mantle to escape from the highly pressurized interior of the planet. This magma fills the gap and eventually erupts onto the surface and cools to form new land. The lava erupting is basaltic, so can travel long distances and create gently sloping land features. This can create huge ridges of undersea mountains and volcanoes, such as the Mid-Atlantic Ridge, where these mountains poke above the level the sea islands have created. Okay. The earthquakes experienced here are usually quite shallow and low magnitude. Okay. I've already said that as well. So here we have the divergent plate margin of 2 continental crusts. So where the two continental crusts diverge, mountain ridges are formed at the plate margins as hot magma forces the crust to bulge. As plates move apart, the brittle crust fractures, forming parallel faults. The areas of the crust slowly subsides between the faults to form a rift valley between the rift mountains. So the most famous example is the East African Rift Valley. It stretches for 2,000 kilometers as a result of the African plate splitting in two and moves apart at 7 centimeters a year. You can have volcanic activity along this type of plate margin. For example, Kilimanjaro in Tanzania is on the eastern edge of the East African Rift Valley, and Kilimanjaro has formed due to the area's thin crust. You can see at the middle of the diagram there, the crust is very thin. This enables magma, as magma rises, the magma was able to push through weaknesses of the thin crust to form a mountain, which is Kilimanjaro. Another example is Iceland. Right in the middle of Iceland, you have Thingvellir National Park, and this is a picture right in the middle of, it's a big national park, but it's a rift valley where it's slowly moving apart. And there's another picture there as well. Okay. At this margin here, we have convergent boundary on the screen now, where two plates move or converge together and the destruction of some of the Earth's crust happens. These margins are mainly found along the edges of oceans, and the majority are found along the Pacific Ocean in what is known as the Ring of Fire, and more about that later on. As oceanic plate, which is denser, is pushed towards the continental plate, which is less dense. The oceanic plate is subducted, so pushed under the continental plate at what is called a subduction zone, creating a deep ocean trench. It is the oceanic crust which sinks down to the mantle, as you can see on the screen there, because it is denser. The subducting crust is pushed down at varying angles. So, for example, beneath Peru is between 10 to 15 degrees, and in Japan, the Pacific plate subducts at 40 to 45 degrees. As it descends, friction, increasing pressure, and heat from the asthenosphere melts the plate. Some of this molten material can work itself up through the continental crust, through fissures and cracks in the crust to collect in magma chambers. This is often some distance from the margin where magma can eventually re-emerge at the surface to create a range of volcanic mountains, or if the plates colliding are both oceanic, a volcanic island arc will result. A great example is Japan, and I'll have a picture for you in a minute. The volcanoes tend to be very explosive because the resulting magma from the subduction is silica-rich andesitic magma. So it's gas-laden and it's explosive. The movements of the plates grinding past one another can create earthquakes. When one plate eventually slips past the other, releasing seismic energy. This occurs along the zone of subduction, and it is here in the Benioff zone, which is called the subduction zone, Benioff zone, where we have a combination of shallow, intermediate, or deep earthquakes. Okay, and that's some information there as well, which I've already said. Fold mountains can result at these margins, where layers of rock within the continental crust, as it crumpled up and is crumpled up and above the oceanic lithosphere. The Andes Mountains are formed this way, where the oceanic plate is moved above the, where the oceanic plate is subducted underneath the South American plate. The Andes also have a trench called the Peru-Chile Trench, which is also known as the Atacama Trench. This ocean trench is approximately 160 kilometers off the coast of Peru and Chile. It's got a depth of around 8,000 meters below sea level, and it's approximately 6,000 kilometers long. It is the result of subduction, okay? And the distance between the Andes and the trench is 160 kilometers, which shows you just how far in distance the oceanic plate subducts underneath the continental lithosphere before mountain building, which is called orogeny, can occur. Here we have the converging boundaries of two oceanic plates, and I've briefly touched on this already. So if the subduction zone is underwater, some kilometers away from the coastline, when eruptions occur, volcanoes build up under the sea and eventually form a chain of islands along the plate margin. This is called an island arc, like in Japan or the Aleutian Islands in Alaska. So the island is an arc because it's curved. Now, at this margin, we have two plates of similar density are forced towards each other, so two continental. Neither plates descend into the mantle because of the similar density of the plates. Instead, the two plates crumple into one another and fold upwards to form fold mountains. At these margins, we get fold mountains and earthquake activity, and a fantastic example are the Himalayan mountains. Here, the Indo-Australian plate is colliding with the Eurasian plate and has done so for millions of years. Originally, there used to be a sea called the Tethys Sea between India and Asia, but over time, as the Indo-Australian plate has collided into the Eurasian plate, it's created huge fold mountains, which is rich in marine, which is sea fossils. The high levels of seismicity here include, for example, the Nepal 2015 earthquakes, the Kashmir 2005 earthquake, and the Sichuan earthquakes in 2008. So we have no volcanoes here, but plenty of earthquake activity. Okay, there's another diagram there of the mountain range. And here we have the Himalayas. So the Himalayas tomorrow will be higher than the Himalayas today. It's still growing due to the converging of the two plates. Okay, as the conservative plate margins are not made, volcanic eruptions do not happen, and crust is not destroyed. Instead, two plates slide past each other in opposite directions, or two plates slide past each other at different speeds. As they move past each other, friction builds up as the plates snag and grind on one another, and parts of the fault line lock. When this stress energy is eventually released, it sends shockwaves through the Earth's crust, and we know the shockwaves as earthquakes. And here we have some information there for you. If the copy of this presentation will be online. And a famous example is the San Andreas fault in California, where the Pacific plate is moving northwest at a faster rate than the North American plate. Indeed, the San Andreas fault separates southwest California from the rest of North America. The relative motion between the plates is around 6 centimeters a year, with the Pacific plate slipping northwest of the North American plate. You should be aware that whilst most volcanic and activity and earthquakes occur along plate boundaries, there are exceptions. For example, the Hawaiian volcanic islands, located right in the middle of the Pacific plate, are formed due to a hotspot. Volcanic hotspots are plumes, which is like an extra hot piece of magma, very simply put. A plume of molten rock which rises from the mantle and causes the crust above it to melt. So the plume lies in a fixed position, and as we're aware, tectonic plates move, and the crust moves along the plume. So as the ocean floor moves along the plume or hotspot at about 5 inches a year, the upwelling lava creates a steady succession of new volcanoes that migrate along with the plate. Okay, so the crust that's directly above the sea level, the crust that's directly above the hotspot melts, which will form a volcano. But as the plates migrate, those volcanoes become dormant and new volcanoes will be formed in its place. So as you can see here, as you go further away from the hotspot, the volcanoes get older. So Kilauea, the world's largest active volcano, is still rumbling because the island has yet to move off the hotspot. Okay. Now I'm going to look at the global distribution of hazards. So as I previously mentioned, nearly all volcanic and earthquake activity occur along the plate boundaries with exception of hotspots. The Pacific Ring of Fire is a volcanic chain surrounding the Pacific Ocean. It's a bit like a horseshoe shape rather than a ring, circular shape. The Ring of Fire is famous for its regular earthquake and volcanic activity. More than half of the world's active volcanoes above sea level form part of the ring. 90% of the world's earthquakes happen along the Pacific Ring of Fire, and 75% of the planet's active volcanoes are found here. Here's another image. So as you can see, it goes from New Zealand up to between Japan, up to Alaska, down California, and then South America. Okay. Tectonic events can be compared using hazard profiles. These allow a better understanding of the nature of the hazards and therefore the risk associated with each. One way in knowing a hazard profile is measuring the magnitude size of the tectonic events. So here we have earthquakes. There are two ways to measure a magnitude of the earthquake, the most common one being the Richter scale. The Richter scale measures the seismic energy of the earthquake, and it goes from 1 till about 10. Okay, it's a logarithmic scale, which means an earthquake of a 5 magnitude is 10 times greater than a magnitude 4 earthquake, which means then that a magnitude 5 earthquake is 100 times more powerful than a magnitude 3 earthquake. You can also use the Mercalli scale, which is a rather arbitrary set of definitions based upon what people in the area feel and their observations of damage to buildings around them. This is useless in the middle of the desert where there are no buildings to collapse, because that is one of the descriptions. So this is quite subjective and is not as commonly used as the Richter scale. As well, the Mercalli scale can vary from place to place as well. The volcanic explosivity index is a measure of the explosiveness of volcanic eruptions. The index is based on a scale of 1 to 8, 1 being very small, to 8 being huge and very rare. The level of eruption is based on the volume of products, tephra erupted, the eruption cloud height, and qualitative observation. So, for example, using the term mega, colossal, or gentle. This is also logarithmic as well. As you can see here, eruption frequency versus eruption explosivity. So, as you can see, the more explosive a volcano is, the less frequent it occurs. Okay, so we've looked at the magnitude of the hazard. You can also look at other factors such as, well, magnitude, we've looked at that, predictability, frequency of the event, duration, speed of onset, and aerial extent. And what you can have here now is an example of a hazard profile that compares two tectonic events. So, for example, the Asian 2004 tsunami with the continuous eruption of Kilauea on Hawaii since 1983. So, magnitude, so red is the 2004 Boxing Day tsunami. As you can see, magnitude is, the red is here, so it's enormous, speed, rapid, duration, short, extent, widespread, predictability, well, predictable, and frequency rare. And as you can see, the Kilauea, the blue one, is quite a contrast. And obviously it's much less of a hazard if the magnitude is smaller, the speed of onset is slow, the extent is limited to that particular area, and is predictable. So here we have the hazard profile for 4 things. So we have the navy, which is the basaltic shield volcano. I haven't gone into the basaltic volcanoes in much detail because that's in 1.3.2, but that's the more gentle volcanoes that's found at diverging plate boundaries. The orangey brown is the andesitic composite cone, which you find at diverging. These are the explosive killer volcanoes. Then you have the subduction zone earthquake, which are usually quite powerful, and then you have the tsunami. Now we'll look at the tsunami, the lilac first, and as you can see, magnitude is usually higher risk. Speed of onset, well, it's very quick. It's quite hard to prepare in advance. So, if it's coming, you have to evacuate quick. So speed, high risk. Aerial extent has the potential to devastate large parts of the region, so higher risk. Duration is quite low, it's lower, doesn't last that long. Frequency, higher risk, and then it doesn't happen that often, so that is that more of a risk. And predictability, higher risk as well. So these hazard profiles, if you make a hazard profile, it enables scientists and the government and councils to be able to prepare for such an event and put mitigation and adaptation strategies in place, which comes later on in the spec. Here we have a bit of a summary, so I'm just going to go through it quickly. So usually frequency, the larger the magnitude, the less frequent it occurs. It's difficult to measure the effect of frequency on the severity of the effect. For example, an area that experiences frequent tectonic events may have mitigation and adaptation strategies in place. For example, volcanic monitoring, education. For example, the Merapi volcano in Indonesia. A totally unexpected tectonic event can bring catastrophic consequences. For example, the population wasn't prepared in Kalari in India in 1993 because Kalari is not directly on a boundary, but it's on a fault, and it completely took the city by surprise, and it caused thousands of deaths. Duration. Duration is for how long a tectonic hazard lasts. It's possible to have huge aftershocks after the initial earthquake. For example, Christchurch 2011, the aftershocks actually caused more damage than the original earthquake, or a series of volcanic eruption. Even though earthquakes can last 30 seconds, the damage they inflict are severe. So areal extent, this is a distribution of the tectonic hazard along a geographical area. Some people may avoid living in a dangerous place, yet some may be drawn to that area for reasons such as fertile soils near volcanoes. Speed of onset, the time difference between the start of the event and its peak. Generally speaking, earthquakes happen without much prior knowledge. That comes up later on in the spec, 1.3.3. And predictability. Even though the seismic gap theory, the gap between the P and C S waves, can increase the possibility of forecasting the big one, in reality, earthquakes are very difficult to predict. I don't have much time to go into that in details, but those features also influence the physical profile of a hazard. Now here we have specialized concepts in geography. I'm not going to go into them now, but a 21st century geographer used these correctly in the correct context to get high marks. If you're unsure how to use them, please ask a teacher. But much of them come up later on. For example, resilience, adaptation, mitigation. We look at them later on when it comes to how we can limit the impacts of an earthquake or volcano or tsunami. Causality is how a process causes an event. So what we've done today. Risk, well, we're looking at who are the risk groups later on in the spec. So these are all things that come in naturally in the specification, but please make sure that you use these kind of terminology and use when you're writing that you've got these concepts in mind. Right. Okay, well, diolch yn fawr. Thank you very much for tuning into this presentation. The last session will be a week today, and I'll be doing that one live, and I will focus on Unit 2, the latter part where we look at the fieldwork skills. So the latter part of changing places. So fieldwork, human and physical fieldwork skills. Diolch yn fawr. Thank you very much.